Thank you for introduction. Good morning. So today, my plan is to draw your attention to some of the states. Of course, here, everybody here knows that almost all states can be represented by some sort of tensor network. But tensor network representable states, by that I mean that some quantum states that can be exactly represented by the tensor network with finite bond dimension. That's what I mean by tensor network representable states. And I'm going to give you a few examples. And I just want to draw your attention to these examples, and I'm going to explain how these examples are related to more familiar states, such as a Kitaev spin liquid, or some other states. So, okay. We know already that, such an example, actually one of the most famous examples is AKLT model, which is already mentioned in the agenda of this workshop. So let me start from AKLT state. So basically, AKLT state is the ground state of AKLT model. So this is one-dimensional spin-1 quantum spin chain. And the important fact here is that we can express this Hamiltonian in terms of projection operator in a very simple way. In terms of projection operator, this is something like I plus 1. 2. And this projection operator is the projector to S tot for 2 state. So as a result, as long as you can make the total spin of nearest neighbor, pair of nearest neighbor spins smaller than 2 for every pair, then you get the ground state. Obviously, the ground state energy is 0. And actually, it is rather easy to realize such a state. The most popular construction of such a AKLT state is we consider chain of spins, each represents spin 1, and we split each spin into 2 Pauli spins. And we form singlets. So these 2 guys form singlet. As long as these 2 guys form singlet, then the total spin can never be 2. Therefore, this condition already guarantees that we get ground state. However, we have to, since we split each spin into 2 spin 1 halves, we have to get back to the original Hilbert space, which consists of only total spin 1 state for each state. So after forming singlet, we apply the some symmetrization operator which projects each site into spin 1 state. So diagrammatically, we can, in order to make this diagram closer to the more familiar tensor network representation, maybe we can draw a diagram like. So I'm basically drawing the same picture again. So we define some singlet. I mean, this matrix, this operator is supposed to make the singlet. And after that, we apply the projection operator to spin 1 state. And this is actually the AKLT state. So this is diagrammatically no. So something like this. So basically, AKLT state can be represented by the diagram like this. So if you redefine this part as a single tensor, then you get the regular matrix product state representation of the AKLT state. So this is rather simple. So here, important fact is that AKLT state can be represented by a tensor network with finite bond dimension. Actually, in this case, 2. And so what is the importance of AKLT state is not just it can be represented by the MPS with finite bond dimension, but it is closely related to more important quantum state, that is a Haldane state. And actually, we know that phase diagram of this Hamiltonian, the phase diagram of this Hamiltonian is something like this. Let's see, here is 0, and here is Here is ferromagnetic phase, and here is another ferromagnetic phase. And this is more complicated trimer phase. And here is dimer phase. And here, we get Haldane phase. And actually, I forgot to mention the particular value of theta, which represents the AKLT state. Tangent theta AKLT is 1/3. If theta takes this particular value, then we can simplify the whole Hamiltonian in this way. That's what I forgot to mention. So that particular value comes somewhere around here. So from this phase diagram, it is clear that the AKLT state is somehow smoothly connected to the Haldane state, which by definition, which comes here. So on the other hand, Haldane state itself, in order to express that state exactly, we need infinite bond dimension. But of course, I mean, even very close approximation, very good approximation can be obtained within the finite bond dimension, but exact representation is something different. But anyway, the important fact here is that the Haldane state, although it cannot be expressed exactly by the finite bond dimension tensor network, it is smoothly connected to AKLT state, which can be represented by the finite bond dimension. That's the first example, which we already know. And so I'm going to try to convince you that there are some 2D analogs for this kind of state. Not defective. Maybe just for later use, is this one. Okay. So the first example is Kitaev honeycomb model. Probably there are many mentions already in this workshop to Kitaev honeycomb model. But anyway, the Hamiltonian, Hamiltonian is something like a constant r equals some dot like this. And alpha is the specifier of the directions, x, y, z. Say alpha, sigma, alpha, r, sigma, alpha, r plus the lattice vector in the alpha direction. And of course, we know that, it is well known that this model can be solved exactly by introducing the Majorana fermion. So by introducing Majorana fermion, we can express each Pauli spin by two Majorana operators like this. And as a result, the Hamiltonian can be mapped to a free fermion system like this. And Aij is actually, by definition, it's operator, but since it commutes with the whole total Hamiltonian, we can regard it as a constant. So that's why the Hamiltonian can be reduced to a free fermion. So important message here is that the whole thing can be mapped to the free fermion. And described by the Ising CFT. Although, I mean, the relationship between, this model and various scaling fields in Ising CFT is not so obvious. But anyway, we know that this system is described by the Ising CFT. Okay, now, maybe I should not dip this thing into the water. Maybe. Oh, this one. Oh, okay, good. Ah, I see. I see. Okay, now I'm getting used to this one. Okay. Okay, maybe I should erase the other one for more smooth transition. Good. Okay, now let me get into the discussion of the loop gas, which is closely related to the Kitaev model. Somehow I keep breaking talks. Okay. Loop gas. Okay. So the question I would like to ask here is, can we construct a tensor network state with a finite bond dimension chi that is essentially the same as Kitaev spin liquid, the ground state of Kitaev honeycomb model, just like AKLT state for the Haldane state? So let me just write down the question I just raised. Tensor network state is finite I that's essentially the same as spin liquid AKLT state for the Haldane state. So actually, we started this project by simply trying to obtain better variational wave function by adjusting many parameters and basically, I mean, all the matrix elements, all the tensor elements in the PEPs. But in doing so, we came to realize that it was vital to ensure the vortex, I mean, flux-free condition in order to get better result. So in the end, we realized that the projection operator is quite crucial. Projection operator to the flux-free state. So let me define projection operator to a flux-free state. It's nothing but the product of all local projection operator. And this is flux operator for each bracket. This is basically the product of 6 Pauli operators, x, sigma, y, sigma, e, sigma, x, sigma, y, something like this. And this takes 2 eigenvalues, plus or minus 1. And this projection operator is supposed to project all states into the state in which the all flux is 1. So the definition of loop gas operator is very simple. Loop gas state is simply we apply this projection operator to flux-free sector to some very simple state. This is a product state in which all spins are fully polarized to 1, direction. Right, exactly. Okay. And if you think about the correlation function of this loop gas state, as you can easily imagine, diagrammatically, this is loop gas state, Qi here, and Qj here. Something like this. And we can easily rewrite this as if it is some sort of weighted average of classical model, namely something like this. And basically Ws here is something like this, and here comes the S. S is nothing but the correction of the eigenvalues of, let's say, Sz, for example. Something like this. Okay, maybe I should draw something else here so that we can reduce the number of times I erase the blackboard. So so basically this is like a classical model already. And the partition function, actually the norm, maybe we can regard the norm of this state, loop gas state. Actually, this loop gas state by definition, this definition is not properly normalized yet. So actually the normalization constant plays the role of the partition function. And partition function is, of course, something like this. And of course, the summation is taken over all possible spin states. And if you remember the structure of this loop gas state, then it can be decomposed into something like this. Here comes the projection operator P, another projection operator P, and this layer is basically 111 state, something like this. And if you remember that the P is projection operator, then we can simply get something like this. Okay, you will see. I mean, I'm coming to that point shortly. Yes. So, okay, I would like to answer answer the question. Okay, what is this thing? Let me see. Just a minute. I forgot to explain what kind of projection operator this can be. So basically, maybe I should write this. Yeah. P, if you remember the definition, P is something like this. And you can expand this summation. If you expand this summation, you get, okay, first, I mean, we extract this factor 2. And let's say NP is the total number, hexagon in the whole system. And then we get, if you take all ones here, then you get 1. If you take just only one of the flux operator from many brackets, and everywhere else we take 1, let's suppose, then we get something like this. And then we get something like, let's say, something like this, and so on and so forth. Of course, maybe 2 brackets are separate from each other. And this is not bracket anymore, but I mean, if you think about the nature of this flux operator, if 2 hexagons are sitting side by side, then the product of these 2 flux operators can be expressed as some generalization of the flux operator to the bigger loop, something like this. So now we are getting closer to loop gas, right? So this is why, the whole business is somehow related to the loop gas. Okay, where were we? Okay, so after all, partition function can be expressed as this. And G here represents the loop gas configuration. Loop gas configuration is a graph which consists only of loops. How many loops, it doesn't matter. It can contain as many loops as possible, as you like. So anyway, the G is, the summation over G is the summation over all possible loop configuration of the whole system. So then what is this weight? Actually, with some arithmetic, it is very easy to realize that this weight here, G is nothing but the volume of the graph. Volume of the graph means that the vertices, the number of vertices on the graph. Actually, this is very easy to realize because, for example, if we have only one loop in the whole system, everywhere else, for example, at this point, this gives you 1. Basically, because this is the product state of the fully polarized state. So if there's nothing in between here and here and the cat, then it gives you 1. On the other hand, at this side, for example, at this side you get sigma z, and on this side you get sigma x. So basically, what you have to know is alpha 111 on each side, and this is 1 over square root of 3. So it is very easy to realize. So this means that the partition function is, after all, beta number of loop config. And actually, this is the simplest case. Actually, there is a family of loop gas model, and more general loop gas model is defined not only by the volume of the graph, but also by the color of the graph. So in our case, we don't have any color. It is just we have loop or we don't have loop. There's nothing else. But in general, for general loop gas model in classical statistical mechanics, we introduce color, how many colors we have for each loop. Yes, right. This loop configuration can be anything. For example, G is like we don't have anything here, and we have another loop, something like this, and we don't have anything else. Yeah. Oh, infinite loop. Infinite loop. Yes, depending upon the boundary condition. If we are talking about the torus, for example, we include, all loops. Yes. Hmm? For example? Oh, yeah, right, yeah. Right. We include all the loops with non-trivial, winding number. Okay. Probably you don't need to go to gym if you are regularly give lectures here. Okay. In our case, beta is square root of 3. 1 over square root of 3. In our case, but for general loop gas model, it is, variable. So let me explain the, for general loop gas model in general. The general loop gas model is defined with two parameters. Maybe I should use beta for consistency. Again, this is loop gas configuration. And beta. Besides this factor, in general, we have this factor. And N loop here is the number of loops included in the graph. So in this case, the number of loop is 2, for example. And this is usually taken to be integer, 1, 2, 3, 4. And there is a literature about this classical model. So if n equals 0, this model is described by the same CFT as self-avoiding work. And if n is 1, this guy is represented by the Ising CFT. And if n is 2, it's xy. So there is known correspondence between the loop gas model with various color number n to more familiar models. And actually, an important fact here is that also on honeycomb lattice, the exact critical value of fugacity is also known to be something like this. Avoiding walk, Ising, and xy. So actually, although at the beginning, we didn't realize that our state is critical, actually it turns out to be exactly critical because this value happens to be the same as the critical value of the loop gas model. So yeah, let me. The loop gas state is exactly at the criticality. Which is governed by the 2D Ising CFT. Maybe. Okay. Okay, and yeah, of course, loop gas state, so far, I have not talked about any evidence which connects, this loop gas state to the, Kitaev spin liquid, apart from the fact that they are both governed by the Ising CFT. So let me show you one evidence, but in order to do that, maybe I have to explain something else. So right now, we don't have any tunable parameter. This loop gas state does not have any tunable parameter. We got 1 square root of, 1 over square root of 3 without adjusting. So maybe we want to introduce some parameter which might connect, this state to the Kitaev spin liquid. So in order to find something like that, we considered the following operator, yet another operator, which we call the dimer gas operator. Dimer gas operator is something similar to the loop gas operator, but the object now is not the loop, but the dimers. The dimer gas operator is like nothing plus something like this, sigma z, or sigma x, or of course sigma y. And of course, we can have any number of these things. And of course, we have a fugacity according to the number of diamonds we have. So in this case, we apply the constant eta. And if you have 2 diamonds, you multiply eta squared. So in this way, this operator is a function of the parameter, 1 parameter eta. And the idea is we apply this new operator to our, loop gas state, and adjust this lambda, adjust this eta, so that the energy of the Kitaev Hamiltonian be minimized. So actually, maybe I can I show the slide? Yeah, numerical result is very hard to show in the blackboard. So let me just show one slide. Okay, good. So this phi is related to this eta by, if eta is tangent phi, something like this. So if eta is 0 or phi equals 0, then this diamond gas operator is just 1. It means that at this point, the state is exactly the loop gas state itself. And by adjusting phi, actually this is the energy expectation value of the Kitaev honeycomb model sandwiched by the state defined by this loop gas state and diamond gas operator multiplied on the loop gas state. And as a function of phi or as a function of eta here. And this red horizontal line indicates the exact value of the Kitaev spin liquid, Kitaev ground state. And here is the energy, expectation value of the energy sandwiched by the loop gas state itself. And as you can see, actually this type of variational wave function is quite good. So the fact is, although we have only one variational parameter, the optimal energy was kind of very close to exact value, maybe, I don't know, less than 1%, I guess. So it was pretty good. And actually, we can multiply yet another diamond gas operator with different fugacity in order to get even better approximation to the Kitaev ground state. And by doing these things, we get, something like that. Actually, this picture only shows that our first approximation, which includes only one variational parameter. But as you see, the optimal situation, in optimal situation, the state is very close to the, at least the energy is very close to the Kitaev spin liquid. Yeah, gapless. So you say that as long as energy is different, the state is orthogonal? Yeah, probably, okay. If you look at, local property, probably, locally, maybe the state is, and as you go to closer and closer, then the region in which the state are, local fidelity is becomes bigger and bigger, probably. Yeah. Actually, I don't have any proof for that right now, but that's what we imagine. I'm sorry, what is the point? Uh-huh. So this is not the excited state. This is a variational state. Uh-huh. Uh-huh. Mm-hmm. Yeah, right. So I don't know. I don't know whether, I mean, this state is this state can be understood as a, some sort of excited state. I'm not so sure, but I don't know. So we did not compare the fidelity, actually, so I cannot say not much more than that. But anyway, yes, I think so. Actually, we can introduce the yeah, but what kind of excited state? Actually, there are all sorts of excited states. Yeah, actually, for example, we can introduce some sort of, a gauge twist, somewhere along the loop, winding around the system in either direction. And in such a way, we can create a kind of global excitation, for example, if you are talking about something like that. But yeah, we can also create local excitations as well. Okay, anyway, so although I'm not 100% sure whether, this state is really the Kitaev honeycomb, spin liquid, at least, these two, Kitaev honeycomb spin liquid and the loop gas state share the same criticality that is governed by the 2D CFT. And as a function of this parameter phi, actually, this is the conformal information, various scaling dimensions as a function of this parameter phi. And all the way from 0 to this optimal value, the critical scaling dimensions do not, change. So I don't know. So maybe there is some objection about the nature of this optimal state, but at least, our view is maybe this is somehow reflecting the true nature of the Kitaev spin liquid. At least this state, Kitaev loop gas state with finite bond dimension, is smoothly connected to that. Okay. Maybe I want to go back to the blackboard. Okay, I'm going to show you second example, which might be less familiar than the previous example, but nonetheless, it is kind of neat because we can get exact ground state of some non-trivial, strongly correlated bosonic system. Okay, so I have already discussed the state, loop gas state with monocolor, just one color. And as I said, such a loop gas state represent the Ising universality class. And I also mentioned that if we introduce the loops with multicolors, we can get something else, another CFT. For example, in the case of two-color loop gas, we are supposed to obtain the XY universality class. Okay, so the question is whether we can construct a model, a short-range interaction model, in such a way that the ground state of such a model is exactly represented by the tensor network with finite bond dimension, and also it effectively maps to the two-color loop gas. And that's the example I'm going to show you by using 10 minutes. Okay. The system is basically Bose-Hubbard model with soft core. And basically, we consider square lattice, but the decorated square lattice. So we have bosons defined on each corner. In addition, we have another species of bosons on the edge. So on the circles, we have AX and AX dagger. On crosses, we have AU dagger. And in order to define the Hamiltonian, we define some mixture of these bosonic operators. So for each X is actually specifying corners. For each corner, we define the bosonic operator dx by this. So basically let's say this is X. For this thing, we define a bosonic operator, which is a mixture of the 5 bosonic operators. And for H, specified by U, we define another species of the bosonic operator in this way. Theta U minus theta X minus U. By the way, this is 1/2. By definition, this is 1. Minus AX. Something like this. So this is BU. So dx is defined in this region, and BU is defined in this region, something like that. So now, if you define these operators in this way, you can easily confirm that these two species commute with each other. BU and dx is 0, no matter how close U and X are. Of course, if they are apart from each other, of course they commute, but even if they are close to each other, they still commute. And by using this property, you can easily get the ground state of this Hamiltonian. I have not defined Hamiltonian yet, actually. Hamiltonian is defined in terms of D operator. Okay, Katsura, Tanaka, Tasaki Hamiltonian is defined by this dx dagger dx plus AU だが AU だが AU minus 1. So this is the definition of KTT Hamiltonian. So I don't have sufficient time for explaining why this ground state is really the ground state of this Hamiltonian, but let me just introduce the ground state of this Hamiltonian. So please believe me that this is the ground state of this Hamiltonian. It's very simple in terms of B operator. This is the ground state of this Hamiltonian. And actually, it is also easy to obtain the tensor network representation of this Hamiltonian. Basically, we can express this Q operator. Let's call this as Q. Then Q can be easily expressed as a tensor network operator. So basically, the Q is, by definition, Q is a product of all B operators. And this is, in this case, this is not the loop configuration, but this is dimer configuration in which for example, in which there is short line here and there. So the rule here is, there must be at least one, one and exactly one short line emanating from the cross in either direction. So this is the example of G is something like this. Yeah, as you can imagine, we will end up with loops because this represents only blah, and we are going to have something similar for ket, and so we have another graph which looks like which is similar to this, and by overlapping such two graphs, we naturally get loops. That's how this system is in the end related to the loop gas model. So basically, what I have told you was the partition function. Again, partition function here is the normalization constant is vacuum sandwiching this Q operator. And as I said, one graph is somehow associated with this Q operator, and another type of graph, here is G, and here is another graph which is similar to this, is related to this one. And by sandwiching, by having these two graphs, you get the whole thing is loop graph. So yeah, anyway, important fact here is that the QG here is QG is tensor network operator with bond dimension 2 equal 2. This is the important fact to notice. The 2 means that whether we have, this wavy line or not. We have 2 choices. So this bond dimension is basically 2 for one graph. So the QG is basically the tensor people with bond dimension 2. And since we have 2 such operators, this whole operator can be represented as a people with bond dimension at least 4. But actually, there is a further simplification with some arithmetics. And in the end, I'm skipping details here. But in the end, you can express this part by a loop gas with bond dimension 3, which means that there is 3 possibilities. One possibility is, for a given edge, we don't have anything. And another possibility is we have, line going into that direction, or another possibility is line going to the other direction. So the direction here comes from the fact that actually you can draw you can introduce the direction here from cross to circle, and this G here is something similar, but suppose this part comes from G, and then another part should come from G prime, like this. So in this way, you can introduce the direction for each loop. So in this way, in the end, what we can get is loop gas model with 2 colors. So this is not good yet. So this KTT partition function, after some arithmetic, but I have skipped all the details to reduce that thing to this thing. But believe me, in the end, we can get G. Actually, this time directed loop configuration and beta G. And if you replace this G by the non-directed loop, we can compensate such a factor by introducing additional factor here in loop. So this is nothing but a loop gas model with 2 colors. Okay, now let me just show one slide. Okay. So, this is the result of the simulation of this partition function. And actually, I had to skip, because of the time restriction, I had to skip the fact that the model as I introduced right now, did not have the phase transition point. Actually, it has a phase transition point, but it didn't have phase transition point in a region which has which corresponds to the quantum system, quantum wave function. But now we got, we have slightly modified the system in such a way that we have two bonds in between two corners. By introducing such a modification, still, this modification does not change the symmetry of the system or essential properties of the system which I have described. So basically, this system is very similar to the system I explained. For just single bond for connecting each corner. So anyway, this is a simulation result, and this is something similar to the structure factor. And as you change the beta, the value of the beta basically represent the hopping amplitude. As you go to larger hopping, then you enter the KT phase, which can be maybe this picture might be easier to explain. So this is a structure factor as a function of beta, and the beta, if beta is large, it means that there is more hopping. So as you go to larger and larger hopping, then you get bigger and bigger structure factor, and there seems to be phase transition near here, but since this is a KT transition, it's a little bit tricky to locate the exact position of the phase transition. But you know that there must be the universal jump for the KT transition. And this is the helicity modulus as a function of beta, and this is the supposed value of the universal jump. And as you see, well, this is kind of quite normal for the KT type transition. So probably if you have some experience in the simulating this kind of thing, probably this looks kind of legitimate picture for the KT transition. So thank you very much. That's it.